One of the biggest problems concerning the global health industry is the increased lack of fresh produce available to people in a certain area. These food deserts occur when a community has no access to grocery stores or farmers markets and can lead to malnutrition. A growing solution to this problem is the use of aquaponics systems, growing your own food in a sustainable and efficient way. You can use a fish tank to add nutrients to help the plants grow. We designed a system that would pump water from the tank to a PVC pipe fixed above the tank. The pipe has small holes in it so the water drips down. We placed a larger PVC tube with the top cut off underneath the dripping water. This was filled with gravel and housed the plants. The second PVC pipe also had holes in the bottom so the water dripped back into the tank. The water makes a full loop, providing the plants with water and nutrients along the way. We used 2 aquatic plants for oxidation and 3 terrestrial plants for food. The aquatic plants were called Amazon sword, Echinoderus griesbachi. The plants growing above the tank were thyme, Thymus vulgaris, parsley, Petroselinum crispum, and aloe vera. Thyme and parsley are herbs often used in cooking, and aloe is a natural remedy for skin problems such as sunburn, but the gel is also edible and nutritious. We used a total of 14 aquatic animals to fertilize the water. There were 2 guppies, Poecilia reticulata, 4 minnows, Phoxinus, 3 goldfish, Carassius auratus, 2 silver mollies, Poecilia sphenops, 1 red platy, Xiphophorus maculatus, and finally 2 ghost shrimp, Palamonetes pallidosus.
As Sam previously stated before, there are a variety of plants and organisms in our aquaponics project. For example, we have aquatic plants which provide oxygen for the fish through oxidation. The plants absorb ammonia, which can be toxic to the fish in high concentrations. The nutrients from the plants are drained back into the tank to help the fish grow. And the fish also contribute to the aquaponics project. They provide carbon dioxide, which is used in photosynthesis. In turn, the plants remove CO2 from the water levels, which reduce pH levels. The fish waste is used as fertilizer for terrestrial plants. There are also certain abiotic factors that play an important role in the project. For example, the constant water circulation will help maintain the amount of water each plant receives. The constant water circulation also provides a steady temperature. This temperature must remain constant as the plants thrive under a certain heat range. If the water is too hot or too cold, the enzymes will denature, resulting in no photosynthesis. The light above the plants is always turned on. These overhead lights are a source of light for the plants, which help contribute to photosynthesis. Our last abiotic factor is the bulb, which is kept at a constant rate, which contributes to oxidation.
Mass-produced food usually produce tons of carbon dioxide and release it into the air. And with this solution, it creates no excess carbon dioxide that is released into the air. It uses nutrients provided from the fish to grow, and the carbon dioxide is recycled throughout the process. The carbon dioxide in this system is always going to be recycled in the process when traveling between the plants and the fish. The fish use the oxygen that is dissolved in the water to respirate. Through the respiration, they release carbon dioxide back into the water, which is then picked up by the plants and used for light-independent reactions to create glucose for the plant, which store energy, allowing the plants to grow. The oxygen that is produced in the plants is released into the atmosphere, and the bubbler can, in turn, eventually take that oxygen and dissolve it into the water so the fish can use it to respirate once again. Nitrogen is the main benefactor in the growth of plants, as it plays a big role in photosynthesis, and the fish provide an outlet to recycle the nitrogen to be used for the plants again. Nitrogen first comes in as food for the fish. They digest the food, and the fish transform it into nitrogen, and it is eventually released through waste. The plant uses the nutrients from the waste of the fish as a reactant for photosynthesis. The nitrogen is eventually drained back into the tank to then be used by the fish. Similar to nitrogen, the nutrients that allow the plants to grow, come from the fish in the tank, both from their waste and or the fish dying and decomposing. But in this lab, we take the fish out of the tank before it decomposes. The nutrients are sucked up by the plant. The main ones of which consist of nitrogen, phosphorus, and potassium. Along with soaking up nutrients from the water, the plants also suck up ammonia, allowing the water to be less acidic, as it would have a bad effect on the fish in high concentrations. Similar to ammonia making the water become more acidic, carbon dioxide in great amounts also creates an acidic environment, making it harder for things to decompose, letting the nutrients continue in their cycle. In the 3 days that we took measurements, the pH started at 7.2, rose to 7.5, then to 7.3 on the third day, and proves that the plants can take the water filtered for them and clean it so it is usable for the fish while also supporting the growth of the plants. Based on how nutrients are recycled in our ecosystem, we can infer that the more nutrients that are used, the faster the plants will grow, allowing for more carbon dioxide to be consumed by the plants, which in turn allow the amount of dissolved oxygen in the water to grow, which also allows more fish, repeating the process since nutrients come from the fish processing food given to them.
There are two energy levels in this ecosystem. The plants act as producers and the aquatic animals are consumers. While the fish and shrimp don't directly eat the plants, energy is still transferred through the nutrients, so both the plants and animals benefit from having the other in the ecosystem. Our aquaponics project can be deemed successful due to the fact that the nutrients are constantly being recycled. The plants provide for the fish in various manners, such as reducing carbon dioxide levels, reducing ammonia in the water, and by providing nutrients. The fish are also beneficiary toward the plants as their waste can potentially be used as fertilizer. Our plants are an example of growth in the system. Over the course of our project, the thyme grew by 5 grams, the parsley grew by 4 grams, and the aloe grew by about 2 grams. If we multiply these growth rates, which are for 5 days, by 72, we get the amount of growth in a year. The yields from these plants would then be 398 grams of thyme, 270 grams of parsley, and 118 grams of aloe. The system we've created is very energy efficient and requires a little electricity to form a self-sustaining, cost-effective, and food-producing environment. Our model is fairly simple and would not take a lot of money to mass produce. Also, the whole setup takes up less than 7 square feet of space. It wouldn't be hard to get a lot of these devices out to a lot of people, in particular to households and food deserts. A much larger aquaponics system would be required for there to be a primary source of food, but using one this size can be an excellent way to get much needed nutritional value. However, our model can be augmented to any size necessary by simply changing the size of the PVC. Aquaponics can really make a difference in struggling communities and help to better the health of humans around the world.